Welcome to this next session of the electromagnetism module. In this fourth session, we will be discussing currents and resistance and a little bit about the Drude model in the end. So let's define the electric current. The electric current is essentially the rate of the flow of the charge. So if we have delta Q charge, which is passing through a surface in a given time interval that we denote with delta T, then this so-called average current, which we denote as I average, will equal to the charge that passes through this A area per unit time. So we define the average current as the ratio of delta Q and delta T. So then we can go into the instantaneous current definition. That's the limit when this delta t time interval is going to 0. So when that happens, then this division of these two small things will become a derivative. Essentially, the current I is going to be the derivative of the charge by time. The SI unit for the current is ampere, which we denote with A. So, and as the definition of the I was the charge versus divided by time, the unit will be the coulombs over second. So let's just consider a segment of a uniform conductor, as we can see it here. And so we say that we have Q charges in this given volume, uppercase Q charges. So that means that we have this uppercase Q will consist of little charges, and which you denote the little q, lowercase q. We have n of these, so we will multiply the lowercase q with n, and then we multiply with the infinitesimal volume. So this volume, with this picture at hand, we can say that this volume equals to the surface area with A, and we multiply that with the length of this cylinder, which is delta x. So now we can just use the information that we can calculate distance if a velocity, which is this drift speed or drift velocity, Vd, is given, then the distance is going to be this Vd times delta t. So we can put that into the place of the delta x. And so this definition of the delta q will be the little q charges, and many of them the surface of the cable, the velocity of these charges, and the delta t time at which we are looking. So now, if we go back to the average current definition, that was the delta q over the delta t. So that means that we can calculate the average current with this formula, which is the same as above, just divided with the delta t. So we get n number of charges times q times a times the Vd. So in this situation, then we just have a cable. There is a random motion of charges. However, if we have some voltage difference between the 2 points, then there will be an electric field, and this electric field will, when you have a charge in an electric field, there is a force acting, and that force is then going to, pull the charges, and they will go in the opposite direction of the electric charge. The next thing to discuss is the current density. So the current density is the situation when we move from this I to the J. So the current density is denoted with the J, and actually that's a vector quantity. But so this J, the magnitude of the J, is understood as the current per area. So if I go back to the definition of I before, this had an extra A in it, so with dividing with A, we just have something that's finally irrelevant, that doesn't contain any information that's irrelevant for the current, like the size of the cable, and like the length of the cable, and the time, and so on. This is all excluded from this current density J. And so the unit of the J is that it's ampere per meter squared, as the definition was that we divided the current with the area. Let's now discuss resistance. So resistance is the situation when we have a current density, and then there is an electric field. in this conductor. And so if there is a potential difference between 2 points of this conductor, and then the resistance will be created. And actually, this here is Ohm's original law, which says there is a relationship between the electric field and the current density. And the things are connected with the sigma, which is the conductivity of the conductor. So J equals sigma times E is the original Ohm's law, and this is something which is not something very fundamental of nature. This is something that is true for certain material, and we call these materials as ohmic materials. And this is something that we just observed. However, we also observe that there are certain materials and devices that do not have this property, and they are called the non-ohmic materials. So it's an empirical law, that's what I just mentioned. It's only true for certain situations. It's something that's connecting two somewhat abstract quantities, the current density and the electric field. And so we can modify this into something which is more practical. And this is going to be the Ohm's law that you are probably already aware. So if we say that this conductor has like a segment of a straight wire, there is a magnitude of potential difference across this wire, then we can say that delta V is going to be the electric field times L, right? So this was, the definition for the potential was the line integral of the electric field. However, if this is a simple situation, homogeneous and in one direction, then this is just going to be the length of the path. So in this case, let's just call it L. So electric field times the L is the potential difference. So if I insert this, right, I express E from this, I divide with the L, then I can put this into the original Ohm law, where J equals sigma times the potential difference of the electric field, from which we modify to the potential difference divided by the length. So we can say that we introduced the J as the current density, which was the current divided by the surface. So if I include this, I get something from the left-hand side, and then I can rearrange stuff so that the delta V goes to the left-hand side. Then I will have the L divided by the sigma multiplied with the J, and then I can also say that the J was the same as I over A. So with this, we have a quantity that we now have I, the current out, and we have this L over sigma A, which we call the resistance of the conductor, and we denote it with the R. And with this, we get that R equals the potential difference divided by the current, and that's the form of the Ohm's law that you are probably already aware. And this is not really the original law, but a direct consequence of it. And we should also add that the unit for the resistance is ohm. This V is supposed to be an omega. I'm sorry, it didn't really came through with the PowerPoint. So the SI units are ohms, and they are volts divided with amperes. So just a little bit of real life again. Most of the electric circuits use resistors. They control the current. They look something like this, and these colors of these bands are very important to figure out what is the resistance of that resistor. So you have the first three colors, the first digit, the second digit, and then you have a multiplier 10 to the power of something, and there is a tolerance. And here are the color codes. So if you see here, we see red, and then more like let's just do this one. This is brown, green. So brown is going to be 1, and then green is 5. So that's 15 times to the power of yellow, that's a 4, so that's 1500 ohms in this resistor. So now that we discussed the resistance, we can discuss resistivity, which is denoted with rho. That's the inverse of the conductivity, which we denoted with the sigma. And so we just figured out that, or actually defined R to be L over sigma A. So if I rearrange that, then I get that this R resistance is going to be the resistivity rho multiplied with these L over A factors that are geometrical factors. So when we have an ohmic material, then they have this property that the resistivity depends on the material and depends on the temperature. There is a temperature range in which the resistivity of the conductor varies approximately linearly with the temperature, and so we can do a Taylor expansion. And in the first two terms of the Taylor expansion, well, actually it's the first term, right? So you have the zeroth term, and then the first term you have that you have some constant factor, and you have the temperature minus the T0 temperature. So we take this T0 usually to be 20 Celsius degrees, and we call the rho zero the resistivity at the temperature. And so this alpha constant that I mentioned is the coefficient of resistivity. So the term above is for resistivity, but we can also have it for the resistance. So actually it just means multiplying with all these factors. So the form is the same. The R, the resistance, is some reference resistance multiplied with 1 plus alpha times the temperature minus the temperature, the, the reference temperature. Please note that this alpha could be negative. There is nothing that would make it have to be positive number. And if it is negative, then we have something which we call semiconductors. And so this class doesn't really discuss semiconductors too much in detail, but we also don't discuss something which is a completely different behavior of superconductivity. Superconductivity means that below a certain temperature, DC, there is no resistance at all, and we can discuss these things at, at session time if you're interested. I think this video anyway will be short. So for the metals, we have a linear slope, almost linear slope. Then we have semiconductors, then the resistivity decreases, and then this linear slope goes up, slowly but up. And then when we have the semiconductors, as the temperature increases, the resistivity decreases. And with the superconductors, as you decrease the temperature, there is a point below which resistivity is gone. Otherwise, they are like the metals. So in this Drude model of the current, we say that we have atoms. So we have a regular array of atoms, and we have free electrons, which we call the conducting electrons. And so we have these two things, which we combine into a system. The atoms and the conducting electrons form a system. And so these conducting electrons can go around. They are free to move in the atom. And so if there is no electric field, then these conducting electrons move in a random direction, as you could see it in the picture earlier. So this is the situation that we call that it's an electron gas. And then when there is an electric field, then these free electrons drift slowly in the direction which is opposite of the electric field. And the drift speed is denoted with the Vd, which is usually much smaller than the average speed. So the average speed between collisions happens around with the speed of a million. This drift speed happens with 10 to the power of minus 4 meters per second. So when we have a collision, then we say that the motion of the electron after that is independent of the motion before the collision. And then we have an excess energy which we acquire due to the work done on the system by the electric field. Then this is transferred to the atoms of the conductor, and the electrons collide, and the atoms collide too. So there is a net force here which we can include and apply Newton's second law. So the acceleration of the system will be the sum of the forces divided by the mass. So what kind of forces are here? It's the electric force. So we calculate the electric force as the charge times the electric field, and so that's the sum of the forces, and then we divide with the mass. Mass of what? It's the electrons, so it's the mass of the electron. We can say that this electric field is uniform and the electron's acceleration is constant. So the electron can be modeled as a particle under a constant acceleration. And if that's true, then the velocity is calculated, the final velocity is calculated as having an initial velocity times this constant acceleration times the time. But we just figured out that this acceleration from Newton's law is going to be this quantity. And now, again, we will just look at a bit about the symmetries of the system. So this vi, the initial velocity of the electrons, is what happens after the collision, and the vf is what is immediately before the next collision. So with the symmetries in mind, we can assume that these initial velocities will be completely random in their direction. So if you sum up these vectors, then this vi will have a length of 0. These vectors will just be a null vector. So then we can get rid of that and say that the average final velocity, which is the drift velocity, is going to be this q times e electric field divided by the mass of the electron times a time like quantity, which we denote with this Greek letter tau, and so this is the average time between two collisions. And so with this, we reach the end of this short lecture. We can discuss semiconductors and superconductors at the session time. Thank you. Bye-bye.